In this video, we are going to see the Nernst equation. In that, we see the first point, electrode potential, which is also called as single electrode potential or a half cell potential. So, in the above discussion, we already see that when electrode or a metal which is dipped into the salt solution, there always exists a difference in potential between the metal and its salt solution. Means the example is that zinc metal which is dipped in zinc sulfate solution and cadmium metal which is dipped in cadmium sulfate solution. In that, the zinc metal and cadmium metals which is having different potential and their salt solution having different potential. So here we have learned to this difference between the potential is different for different electrodes. So the single electrode potential is defined as the single electrode potential or a half cell potential is the difference of potential between the metal and the solution around it in equilibrium. So it depends on nature of the metal, concentration or activity of ions in the solution, third temperature, and also it depends on pressure in case of a gas. These are the some four different terms to depends on the single electrode potential or a half cell potential. Also, the single electrode potential which is considered as the oxidation potential and reduction potential. Let us see what is oxidation potential and what is reduction potential. We see the first oxidation potential. It is represented as EOX and it is defined as it is a difference of potential between the metal and the solution around it in equilibrium due to the loss of electron. Here we see due to the loss of electron or due to the oxidation, it's called as oxidation potential. And another one, we see the reduction potential. It is represented as ERED, E reduction. It is a difference of potential between the metal and the solution around it in equilibrium due to the gain of electron or due to the reduction. It's called as reduction potential. So in that, we see the reduction potential of an electrode is equal to the oxidation potential for the same electrode between the sign reverse. Means reduction potential of electrode is equals to oxidation potential, but only the sign is reverse. Means here we see that E reduction is equals to minus E oxidation and its potential is 0.337. Another, if it will be represented as E oxidation is equals to minus E reduction and it will be oxidation potential is that minus 0.337. Means remember that the reduction potential of the electrode which is equal to the oxidation potential, but only the sign is reversed. Okay, we know that any electrochemical cell which is made up of two half cell reactions. In that, means we see that one is the oxidation reaction, another one is the reduction reaction. Means one electrode shows the oxidation electrode potential, another reduction potential electrode. So we know that the E cell is equals to E oxidation of left hand electrode plus E reduction of right hand electrode. It will be also represented as E cell is equals to E oxidation of left hand electrode minus E oxidation of right hand electrodes. Here we see the E cell is equals to oxidation plus reduction. It means that the anode plus cathode. For if we consider the single value of single electrode potential for the electrode reaction, it will be represented as M is equals to M n plus plus electron for oxidation. We considered here the single electrode potential means half cell potential. Suppose if we consider the cadmium and zinc electrode, in that the half is represented as zinc, half cell is represented as zinc electrode and half cell is represented as cadmium electrode. Same as if we consider the single electrode potential, in that we consider the oxidation M is equals to Mn plus plus electron. For this reaction, it is given by the Nernst equation, that is E oxidation is equals to E standard oxidation minus RT upon NF into ln A plus. In this equation we see that the sum terms, that is we see the E standard of oxidation, it is represented as standard oxidation potential. Here we see the R. This R is represented as a gas constant and its value is 8.314 joule. Also here we see the N. This N is represented as number of electrons involved in oxidation reaction or a oxidation process. F is represented as a Faraday's constant and its value we already know that 96500 coulombs. Okay, this is for the oxidation Nernst equation. In another, if we consider as the reduction Nernst equation, it is represented as Mn plus n electron, it use the M. It is the reduction process, and in that the Nernst equation is represented as E reduction is equals to E standard reduction minus RT upon NF ln 1 divided by A plus. Also in this equation we see that the E standard reduction, it is represented as the standard reduction potential. R is the again gas constant, is the temperature, and is represented as number of electrons involved in reduction process. F is represented as Faraday's constant ln 1 divided by A plus. This A plus is the activity of cations in the solution. Activity of cations in the solution. In these two equations, this Nernst equation and this Nernst equation, if we consider these two equations, here for the dilute solutions the activity can be replaced by concentration term. This activity which is considered in a concentration term means if we considering the value of R, F, we consider the value of R and F. We know that the R value is 8.314 joule and F value is 96500 coulombs, and we also consider the value of ln. The ln is equals to, we consider 2.303 log to the base 10, and we consider the temperature at 25 degrees Celsius, means if we consider in a Kelvin, that is plus adding 273 we get the 298 Kelvin. That is, if we consider all this value, we get the next equation is that E oxidation is equals to E standard oxidation minus 0.059 divided by N log to the base 10 A plus. This is for oxidation. And for reduction, E reduction is equals to E standard reduction minus 0.059 divided by N into log to the base 10 1 divided by A plus. These are the Nernst equation for the concentration term, and these two are the Nernst equation for activity term. Also in general, the Nernst equation can be also stated as E oxidation is equals to E standard oxidation minus RT upon NF ln A oxidant divided by A reductant, and another one E reduction is equals to E standard reduction minus RT upon NF ln A reductant divided by A oxidant. Second, we see the standard electrode potential, which is also called as oxidation reduction potential. We already see that the Nernst equation and the standard electrode potential, which is represented as the potential of the electrode when activity of its own ion in which solution in which the metal is immersed is unity. Also, this standard electrode potential takes the two forms. First is the standard oxidation potential, which is represented as E standard oxidation, and second the standard reduction potential, which is represented as E standard reduction. So the standard oxidation potential is the potential of the electrode due to oxidation when activity of its own ion in solution in which the metal is immersed is unity. Second, the standard reduction potential it is represented as the potential of the electrode due to reduction, which the activity of its own ion in solution in which the metal is immersed is unity. In that we already see that the oxidation potential and reduction potential, which will be the equal and opposite sign. So the E standard oxidation, which is equals to the minus E standard of reduction. Also it is represented as E standard of reduction is equals to minus E standard of oxidation. Next term we see in the Nernst equation is that the Nernst equation for cell potential. In that we considered as the Daniell cell. We already see the Daniell cell in detail. In that we already see the zinc metal which is dipped in the zinc sulfate solution and copper electrode dipped in a copper sulfate solution. So here we consider the two electrodes and their salt solution. Zinc dipped in a zinc sulfate solution, salt bridge, and copper dipped in a copper sulfate solution, and we get this cell reaction, that is Zn minus Zn2 plus Cu2 plus Cu plus. In this cell potential reaction we see the oxidation reaction and reduction reaction. At the anode we see the oxidation reaction takes place, that is Zn gives the Zn2 plus 2 electron. According to the Nernst equation, the oxidation electrode potential, which is given as E oxidation of zinc electrode, which is equals to E standard of oxidation of zinc electrode minus RT upon 2F ln activity of Zn2 plus ion. Here we considered as the N is equals to 2. We know that what is N? N is the number of electrons involved in oxidation process. So here the 2 electrons, therefore we can write N is equals to 2. Means we get this Nernst equation. So in the another half cell we obtain the reduction reaction at cathode, means we obtain the Cu2 plus 2 electron, it gives the Cu. And according to the Nernst equation, the reduction electrode potential will be given as E reduction of copper is equals to E standard reduction of copper minus RT upon 2F ln of 1 divided by A of Cu2 plus. So in these reactions we see the two half cells. One is the reduction potential, another one is the oxidation potential, and if we combine these two half cells, that is E cell is equals to E oxidation plus E reduction, that is the oxidation potential of zinc electrode and reduction potential of copper electrode. If we combining these two half cells, we get E cell is equals to E standard oxidation of Zn minus RT upon 2F ln A Zn2 plus. This is the one of the half cell. Another half cell is that E standard reduction of Cu minus RT upon 2F ln 1 divided by A Cu2 plus. We add these two half cells. Then if we combining the E standard Zn2 plus E standard reduction of Cu, and remaining in the bracket is that RT minus RT upon 2F ln A Zn2 plus divided by A Cu2 plus. In this equation we see that E standard oxidation of Zn plus E standard reduction of Cu, this will be equal to E standard of cell. There E standard of cell. So we get the equation is that E cell is equals to E standard of cell minus RT upon NF. Here we also write the 2F ln of A Zn2 plus divided by A Cu2 plus. This is the standard cell potential. Also, if we considered for any general cell reaction, that is if we considered as the general cell reaction, that is A moles of A plus B moles of B plus ... it gives us C moles of C plus D moles of D plus ... In this case, the cell reaction it will be obtained as E cell is equals to E standard of cell minus RT upon NF ln of A raised to C base C into A raised to D base D into ... divided by A raised to A base A into A raised to B base B into dot dot dot. This is the Nernst equation for any general cell reaction, and in here we see this cell reaction. This is cell potential, standard cell potential. This is by according to the Nernst equation. Thank you.